Hi, this is Dr. Green, and we are doing a little bit of review for midterm here. So I thought there were some questions on the midterm that either we didn't have homework examples for, or that it would be helpful for you to see some worked problems. So let's go ahead and take a look here. So in problem number 1, they ask us the glomerular filtration rate, or GFR, is a measure of kidney failure. And these GFR values are assumed to have a normal distribution, so that's important. That's a mound-shaped curve, and they've got a mean of 74.9 and a standard deviation of 27.4. And then they want to know what proportion of the patients would have GFR values exceeding 90. So if these have a normal distribution, then we want to figure the z-score that's going to go with this value of 90. So they tell us our mean is 74.9. So let's go ahead and record that information. Record what we know. So mean is 74.9. They tell us standard deviation is 27.4, so sigma is 27.4. And then they want to know how many of the GFR values exceed 90. So 90 is an individual data value, that's our x. And then what we want to do is, on the bell-shaped curve, we want to know what proportion of the values exceed 90. So if you sketch a picture of what's going on here, got this bell-shaped curve, and the mean's at 74.9, so right in the middle here is 74.9, our mean, and then 90 is up here somewhere. And then we can tell from the normal distribution table that's in the back of the book what proportion of the values are above 90, but we first have to find the z-score that goes with 90. So a z-score of 0 corresponds to the mean, or 74.9. We want to know what's the z-score that goes with 90, and then we'll be able to tell that percentage, this percentage here. So the z-score is the difference between the data value and the mean divided by the standard deviation. So for us, that's the 90 minus 74.9, and then divide by the 27.4. So key that into your calculator and then round to 2 decimal places, and if you do, you get 0.55. And so what we want to know is this. We want to know the probability that x is greater than 90, and we have to convert that to a probability question about z-values, or a proportion question about z-values. So that corresponds to z-scores being greater than 0.55. Because on the curve here, now this question mark, we can fill that in with 0.55. Okay, so now we can go to the back of the book and we can find the area that corresponds to that. So let's switch over to that table. So here's the table. This is table 1, probabilities for the standard normal distribution. And the table entries tell the probability or the proportion of scores that are less than a particular z-value. So and our probability here is actually written in terms of a greater than. It's probability that z is greater than 0.55. So that would be to the right of the z-value, but the table tells the amount to the left. So what we need to do is the table's going to give this value right here of all this area to the left, and all of the area has to add up to 100%, or 1. So we got to look at the opposite proportion. So 1 minus the proportion of z-values that are less than 0.55. That's what the table value will give us. So that's going to be 1 minus, and now we find 0.55 in the table. So these are negative z-values, so we're going to scroll down here till we get to the positives. Okay, 0.5 and 0.05. So we intersect those row and column. So 0.5 row, 0.05 column. They add up to 0.55. 0.7088 is that value. So this is 0.7088. And if you subtract those on the calculator, you will get 0.2912. So 29.12%. So that's the proportion of the data that's above z equals 0.55, which corresponds to the proportion that's above 90. So next they ask us GFR values that are below 60 indicate kidney disease. So if your kidney function is below 60 by this measure, you have kidney disease. We want to know what's the probability that a randomly selected patient has kidney disease. So probability, again, is still asking about area under the normal curve. And so below 60 is kidney disease. So what we want to know is we want to know the probability that x is our random variable, the GFR value. We want to know what's the probability that x is below 60. And so, well, we got to find the z value that goes with that again. So we know what our mean and our standard deviation are from up above. Our mean was 74.9, standard deviation is 27, but now our x value is 60. So mean 74.9, standard deviation 27.4, and now the x value we're comparing to is 60, and we've got to find a z-score that goes with that. So the distribution now looks like this. 74.9 is in the middle, 60 is down here, z-value of 0 here. We need to find this z-value, and then we need to find the area to the left of 60, which corresponds to the probability. So areas under the standard normal curve are proportions of the data or their probabilities. So data value minus mean over standard deviation, so this will be 60 minus the 74.9, and we are now dividing by our standard deviation, 27.4, and that gives us a negative z-value. If we round it to 2 decimal places, which you always do with z-scores, negative 0.54. So the probability that x, our GFR value, is less than 60 is the same as saying the probability that z is less than negative 0.54. So now we go back to our table and look up negative 0.54, and this is already a less than, so we don't need to look at the opposite probability. See, this was a greater than, so we had to write it in terms of a less than, because the table only gives less thans. So let's go back up here and find negative 0.54. So negative 0.5, and this would be 0, 1, 2, 3, 4, right there, 2946. So then this value is 0.2946, and that's this value here, 0.2946. Or if you like percents, 29.46%. And either way is fine. And notice here this 29.46% of the values here are below 60, which corresponds to a z-score of negative 0.54. Negative meaning it's below the mean, and then 0.54 is the number of standard deviations below. But notice that since 29% of the GFR values are below 60, that means that the number 60 is in the 29th percentile. Notice it's not the 30th percentile because 30% of the values are not below 60, but 29% are. Okay, a little more than 29%. So in one question they ask you to find the percentile. that corresponds to the value, so that's just the percentage that's below. So find your z-score, find your percentage that's below or your probability that's below, and then that number, that area, is going to tell you what percentile you're in. And then part C, now they're saying here, well, if you've got a GFR below 15, that actually indicates kidney failure. And then they ask us, well, what is the first percentile for kidney function? And is that in the range that corresponds to kidney failure? So in other words, the first percentile, is that below 15? Okay, well, what we want to do here is we want to, with our mean 74.9 and our standard deviation 27.4, what we know is if you're in the first percentile, then the area below the x value is 0.01, 1% of the area is below. So if you sketch your diagram here, you've got your 74.9 in the middle, and then down here in the first percentile, you've got this value here that we're trying to find right there. And what we know is we know that that percentage, that proportion or probability of area, 0.01. Well, areas are what's given in the body of the table. So if we go back to that table, what we want to do is we want to find the closest number to 0.01 out here in the body of the table, and then we can go across and up here to find out what the tenths and the hundredths place are for that. So 0.01, let's see, closest value, see, 0.057, 0.0099 looks like right there. That's just a little bit less than 0.01. This is looks like 2 10,000ths greater, and this is 1 10,000th under. And that corresponds to a negative 2.33. So the z-value here is negative 2.33. So again, from table 1, the closest value to 0.01 in the body of the table is 0.0099, and that corresponds to z equals negative 2.33. So that's what we found from the table. And then the first percentile, the x value that goes with it, this formula is in your book. It's the mean plus the z-value times the standard deviation. So our mean is the 74.9, and then plus our z-value is negative 2.33, and then standard deviation 27.4, and then you plug this into your calculator and compute. And if you do that, you will get 56.2. So 56.2 is the value that's right here that corresponds to the first percentile, or 1% of the data is below that, 56.2. So then they ask this question, okay, well, is the first percentile, is that in the range that corresponds to kidney failure? Well, kidney failure is below 15. This is up at 56. 15 is going to be way down here somewhere. There's 15. So no, this is not in the range for kidney failure. Kidney failure is GFRs that are to the left of 15. They're less than 15. So since kidney failure occurs below 15 and the first percentile cutoff is not in that range of below 15, answer is no. Kidney failure is below the first percentile. So actually, when your GFRs get that low, it's very low in terms of comparison to the rest of the population. So that should help you out actually on more than one question. In question 2, we're given some data here that summarizes the gender distribution for some diseases: stroke, diabetes, cardiovascular disease, by male and female. So we've got row totals here, column totals here, grand total of 374. And they ask us first a general probability question. What is the proportion of the sample that have cardiovascular disease? So, well, that's going to be there's 73 that have cardiovascular disease. That's the number, and that's out of 374. And we're assuming it's equally likely that you'd pick any one of those 374. So this is 374 is our total, and out of that total, 73 had cardiovascular disease. So this is CVD out of the total. And to 2 decimal places, that is 0.20. It's actually 0.195, but we'll round to 2 decimal places here. Next up, what is the proportion of diabetics that are female? So it's of diabetics, so it's given that they're a diabetic, and then of those we want to know what proportion are female. So this is going to be proportion of female given diabetics, so the vertical bar there means given, and remember that the given condition restricts your total outcomes, so we're restricted our total outcomes to just diabetics. So people with diabetes were 220, and of those diabetics, the females were 96. So out of that column of 220, we had 96. And then 96 out of 220 to 2 decimal places is 0.44. And then lastly, what is the probability that a male, so we're given that the person is a male, is a stroke victim? Okay, so this is asking what's the probability that they've had a stroke given that they're male. So again, the given condition determines the total outcomes in the denominator. That is male, which there were 200 males. And then out of that 200, how many also had a stroke? So there were 44 strokes from the males from that 200. So 44 out of 200, and as a decimal, that is 0.22. Number 3 here, we're looking at fatty liver disease. The risk of that among alcoholics is 0.32 or 32%. Suppose we have 10 alcoholics. What is the probability that exactly 4 of those 10 people have fatty liver disease? So this is a binomial probability because you either have the disease or you don't. Okay, so it's binomial because it's a yes-no. And so we're going to use the binomial probability formula. So our probability that any one randomly selected alcoholic would have fatty liver disease is 32% or 0.32. So our P is 0.32. And then N, we're going to observe 10 alcoholics. That's our sample size, N. And then we want to know what's the probability exactly 4 of 10 have fatty liver. So that's probability of 4 successes, or you might just write it as probability of 4, or x equals 4. And then remember what you do is you have to do combinations of 4 from 10. So that 4 factorial goes up on top. No, I'm sorry, the 10 factorial goes up on top. And then down on the bottom, we've got the 4 factorial, and then 10 minus 4 is 6 factorial. So these two numbers have to add up to the 10. And then you take your probability of success, which is 0.32, and then the power on that is the 4, and then times 1 minus 0.32, and the power on that piece is the 6, 10 minus 4. And then we enter this into the calculator. So let's see if we, and I'm pretty sure you can enter this into the MyScript calculator just like I've got it written on the page. So should find that very helpful. So I entered this in, and I got 0.2177 to 4 decimal places, or 21.77%. So approximately a 22% chance that exactly 4 out of 10. So that's binomial probability. And then number 4, let's see, following table shows results for screening tests that's hypothesized to identify people at risk for a rare blood disease. So our results are divided up whether the screen was negative or positive, and then whether or not the disease was present. I've got column totals and row totals here. So first they ask us compute the sensitivity of the test. So remember, sensitivity of the test is the probability that the screen was positive given that the disease was present. Okay, so this is a given condition. Remember, this vertical bar means given. That's a conditional probability. So they have the disease, that's the given. So you look at the disease column, that's 67, that's our denominator. So the given condition determines the denominator. Now, out of those 67, how many had a positive screen? Well, screen positive is this row, that's 52. So 52 out of the 67. And let's see, I got 0.7761. So there's our sensitivity. And then they ask specificity, which is the probability that a random individual would have a negative screen when they were disease-free. So that's a true negative. So we got a true positive, a true negative. And so it's given that they're disease-free. Okay, so no disease. There were 1,208 people total. So 1,208. Again, this is our given condition. Now, out of those 1,208, how many had a negative screen? And that was 1,120. So 1,120 out of 1,208. And if you divide that, get the decimal for that, it's 0.9272. So there is our specificity. And then they also ask us the false positive fraction. So false positive, remember, is the probability that they got a positive screen when they were disease-free. Okay, so the test did not give the correct result. They do not have the disease, but the test said they did. So it's given that they're disease-free. You can't have a false positive unless you don't have the disease. So that's, again, this 1,208. So our denominator is 1,208. And then out of those 1,208, how many had a positive screen? So out of these 1,208, positive screen were 88. So 88 out of 1,208, excuse me. And let's see, if we divide that one, and you will get 0.0728. And then next here, they want us to compute the false negative fraction. So false negative is going to be when the disease is present, but the screen is negative. So it says the disease is not present when it really is. Okay, so it's given that the disease is present, so we have disease, so that's 67 total, so that's our denominator. And then out of those 67, how many had a negative screen? And that was 15. So 15 out of 67, and that is 0.2239. And then in one of the questions, they also ask, what is the positive predictive value, or the PPV? That's defined to be the probability that the disease is present when you got a positive screen. Okay, so it's given that you have a positive screen, so we're only looking at people that have a positive screen, which is 140, and then out of those, how many had disease present? 52. So 52 out of 140. So 140 is our total. That's the positive screen. out of that 140, disease was present in 52. So 52 out of 140 is 0.3714. And then to finish up, we will ask the negative predictive value here, so NPV, and that's the probability that a person was disease-free given that they had a negative screen. Okay, so we're only considering negative screens, and then out of those, how many were disease-free. So negative screens were 1135, and the ones that were disease-free were 1120. So 1120 out of 1135. And if you divide that one, you will get 0.9868 to 4 decimal places. 9868. There we go. Okay, so hopefully that will help you do all of the questions that maybe I didn't have examples for in the homework, in earlier homework, or that I thought you might have trouble with on the exam.